Hey everyone, so welcome to this recording of basically covering the stuff that I covered during my methods lecture back in a month or so ago from the time of recording. Hopefully all of you guys have settled back into school by now. You're gonna have a better idea, or at least a somewhat better idea about what your QCE year will be like, what you have to go through, and also some of the stuff that you're going to be covering in your math subjects as well. The main aim of this recording is more or less for the many of you who are not able to make it to the lectures because of reasons I assume out of your control, obviously. Just to give you guys a bit of a taster of the stuff that you missed, and if you've already been to the lecture before, you can always just use this recording as a bit of a refresher along the way. So, most of the stuff that I'm going to be covering will be, at the very least, compared to my actual lecture at a much faster pace. But please bear in mind that because this is a recording, you may, of course, choose to just pause it every now and then and just step back a bit, think about what it is I'm saying if you don't understand it, and then try to come back to the recording once you get it. Of course, if you have any troubles with that, please jump onto our forums at atarnotes.com, atarnotes.com on the end, for just that, and you can always ask me about it there. But otherwise, for the most part, I'm going to get into it soon. But just before I do, I probably don't know much about who we are, who ATAR Notes is, what we do. And to put simply, our goal is more or less just to make education more accessible to you guys. If you jump onto our website, atarnotes.com, you'll find thousands of downloadable notes already available to you. Of course, lectures, we'll have more of that throughout the year. And our forums are right there available for you. We have some videos available, and also, as soon as you register for an account, you get subscribed to our newsletter automatically, and our team, I personally don't know what they put themselves, but they put a lot of really valuable stuff that you guys should read in your own time, if you have the time to. We also have some articles about little minor things that involve not just methods, but any subjects that you study, and also bits and pieces about the QCE in general, and also some other stuff that you may want to check out in your own time when you're able to. Of course, our most important things that we offer to you guys are available in our shop. They are our study guides. These are essentially summary notes covering essentially everything you need to know for the course. It targets everything you need to know and also nothing that you don't. And right now, these are the titles that we're selling right now, and we also have some more coming in the future, like, for example, literature and physics, I believe, will be coming up. And for those of you that already know what text you're going to be studying for your English subjects, we also have some text guides. And these are more or less just very compact but comprehensive breakdowns of what you need to know about each of these texts to, of course, write in your essays and analysis and so on. Also, we have an unlimited for the people that prefer not to go for the paper version and prefer the online ebook version instead. Some people like to view this as, from what I've gathered, a Netflix for education. I don't know what that means, but sure. To my knowledge, this code that's available here right now should still be working. So what that means is that you can basically make an account and you can try an unlimited out yourself for free for 28 days. And, well, yeah, hopefully you will enjoy it because it's basically everything you need all in the one go. And it also has benefits in that you get access to the study guides from the other states as well. So if you're looking for even more resources from what's already offered to you in the QCE sections, in the Queensland sections, you can take a look there. And we also have TuteSmart, which is our tutoring program that we hold at QUT, also where we held our lectures, just in different rooms obviously. And for $44 per week for one subject, you receive basically everything that you can see here. And you can check out the pricing online at our TuteSmart website, but the idea is that the more subjects you enroll in, the more the cost scales down and the more cost efficient it is for you guys. So that's something definitely you should check out when you can. Keep in mind, there's also, right now, we are offering a try TuteSmart for 2 weeks. You can pay a deposit through this link, and if you find that you don't want to partake in TuteSmart anymore, that deposit can be refunded with no extra things you need to do. So check it out, and hopefully you do enjoy it, but if you don't, there's always that option available to you. Anyway, so I know you guys are here more for the content, so I'll jump back into it now. I want to mention, when entering Unit 3 and 4, first of all, best of luck. Remember that this is the year that counts. So no matter what happened in the past, if your year didn't go well, don't worry too much about it. But in saying that, if your year did go well, then of course you're probably heading down the right track. Just keep up your nice studying habits or whatever you do to do well this year. And if you didn't do so well, then this is your year to actually, make it count. So pick it up from there. And this is more or less the summary of the stuff that you've done in Units 1 and 2. And as you can see, it's quite a lot of stuff, to be honest. What happens to it? Well, you got to keep in mind that QCAR will now treat this as all assumed knowledge. So they assume that you automatically know how to do this stuff. I wouldn't say you would necessarily not be intimidated by it, but at least you will be comfortable using it if you ever had to again. That doesn't mean the content explicitly will be examinable, it's just that you might use things here and there that require the content that you learnt in Units 1 and 2. Mostly because you'll find that Units 3 and 4 build onto Units 1 and 2 for the most part. Quite a lot. So pretty much in my lecture, well, at least on the day, I covered a lot of work involving logs, i.e. this thing. No, I'm just kidding, that's just a bit of a joke. I covered most of the stuff using logarithms, and I did get a bit of time to spend on calculus of exponential functions. I didn't get time to cover the calculus of logarithmic functions, and hopefully I'll do a bit of that in this recording for you guys. And other than that, this is more or less everything else that you're going to see in Unit 3 anyway, so it's quite a lot of content, but you'll get through it, I know you will. And for the most part, I designed my lecture because hopefully you guys all know by now that you'll be sitting 2 papers, a technology-free exam where you have no calculators, a technology-active exam where you do have a calculator. Most of the stuff in here assumes that you don't have a calculator available. Anyway, so not going to spend too much time on this. More or less, I'm just hoping that before jumping straight into logs, you guys are all comfortable with your index laws. So for example, if I show you something like this, you will be comfortable with combining coefficients and combining the powers. Again, remember, pause the recording if you need to, but I'm going to move on relatively quickly from this stuff. Similarly, for even more complicated examples, so long as you just fight through it a bit more, it's generally expected that you will be able to come to the end result without much of a hassle. And there are also other results involving reciprocals and fractional powers. Just remember, negative powers means reciprocals, and fractional powers means thirds, like nth roots. And also little things like this here and there. As long as you're comfortable with seeing them now, it's all fine. And that's another fancy question. And I also wanted to remind you guys, well, where did logarithms come from? Well, the idea is that if we were solving index equations, some of them could be very well possible by just identifying powers of certain numbers very easily. So for this question, you could just see that, if you knew that 3 to the power of 6 was 729, then you'll be able to solve that equation nonetheless, which is still doable without a calculator, just probably a bit annoying. But then if you have something like 3 to the x equals 2, well, at least no integer or any obvious fraction is not going to satisfy that number. So what do? Is that we sort of introduce logarithm as a bit of a placeholder object, and the idea is that the power that we're seeking, x, becomes the solution. The 3 is moved into the base of the log, and the 2 is what's going to be contained inside the log. So that's a bit of a recap, and this is more or less basically what happens in general. And remember, this is on your formula sheet, so if you ever forget this, please check your formula sheet out. I know in New South Wales, because they didn't have this on the formula sheet, a lot of people forgot about it in the exam, so definitely, don't fall into that trap because you guys do have the formula sheet. And there was also this thing about the inverse relationship of exponentials and logarithms, and from what I gathered in the lecture, not many of you have seen this before, but it more or less is a way of generalizing how, it relates the concept of inverses in that you can see how subtraction is more or less the opposite in some sense to addition, just as how division does the same thing with multiplication. You can have a similar relationship for exponentials and logs as well, and I do use this every now and then throughout the recording, so you might want to copy these down. But it basically says that if I take a power of the corresponding logarithm, I get back to the number that was just inside the logarithm. And here, if I take the logarithm of an exponential, well then the power becomes the answer. Provided, of course, the bases are the same. Notice how I'm using base A for both of them and not, base B or C anyway. And, pretty much the question is, what else do we need to know? So, in Unit 3, the first thing they introduce are now your logarithm laws, and logarithm laws do somehow correspond to the index laws that you saw previously. Like, it turns out that each logarithm law is related to an exponential law, or at least the main ones. These formulae are all on your formula sheet, so you will be given them in the exam. It's basically a matter of you to know how to use them. So for example, as a quick easy question, well, not necessarily easy, but straightforward. Say you wanted to compute this expression when you have a log base 6 of 4 plus a log base 6 of 9. If you had these things by themselves, you would not be able to compute them. But if you use the logarithm law, you will see that they will combine to give you log base 6 of 4 times 9, using the first log law here. And that will give you 36. And you identify that 36 is literally just 6 squared, so the answer is 2, using what you know from logs from units 1 and 2, hopefully. And then the next question, I have a simplified question, and the idea is that if I want to simplify a logarithmic expression, what I basically want to do is use my logarithm laws to tear the thing apart. So I sort of use these laws backwards in some sense. And once you get used to log laws, you'll see that whenever you see a fraction, you basically replace it using the minus log law. And wherever you see powers, you move the powers in front. But this one here, you might need to spend a bit of time on. The fact that log base c of c to the 5 is just 5 itself. Spend a bit of time on this, make sure you really understand why that's true. I won't go into much depth right now, because I do want you guys to do a little bit of thinking throughout the recording. And then you might get questions that more or less involve logarithm laws in more subtle ways. So this question basically says, well, given some approximations, can you now estimate a different log? So you're given the approximation for log base 5 of 2, which you can see that I used in this line. And you're also given the approximation of log base 5 of 3, which I used down here. And the idea is that they are more or less useful because the trick is you can decompose 18 into 2 times 3 squared, which is really a product of a power of 2 and a power of 3. 2 and 3 being very rigged choices because, yes, they showed up here. And so you obtain that. And the idea is that whenever you see a product using a log law, you can decompose it into a plus. And whenever you see a power, you can always take the power out in front and turn it into a coefficient. And then once you do that, you can now more or less use the approximation that you've been given to arrive at your final answer. Cool. And then you also have the opposite of this kind of question. So this question more or less made you tear the logarithmic expression apart. This instead is now more or less asking you to put everything all back together. And the tough part about this question was more or less identifying that 1 could be written as log base 5 of 5. Again, that you should think about to see why that's the case because, 5 to the power of 1 is 5, so log base 5 of 5 is 1. That may have been a bit rushed, I do apologize for that. And you also have these little things here. The coefficient of 1/2 gets moved into the power when you want to go back the other way. And then more or less, when you have a whole bunch of pluses, you can basically replace them all with a whole bunch of times. So you get a log base 5 of 5 times a times b to the 1/2. And notice how I just rewrote b to the 1/2 as the square root of b. There are some other log laws that are not explicitly mentioned on your formula sheet, but these are, the reason why I believe these are not mentioned in formula sheets are because usually you should be able to figure these out on the spot, or what I really mean by that is that the other log laws should be able to help you with deriving these ones. But personally, I felt that memorizing these has saved me a little bit of trouble throughout my experience with maths, both in high school and at university. So if you have the time to try to remember these, but if you don't, so long as you can remember little derivations like this, which do take a bit of time to think about intuitively and they'll make a bit more sense, but as long as you can try to figure these derivations out on the spot, I reckon you will be okay. And then basically I thought, well, okay, so you've seen how to use the logarithm laws, but a natural question to ask is, well, can we at least prove one of them so that you're convinced that the log laws are actually reasonable log laws and not just some random thing I plucked out of thin air and I'm expecting you to believe it? And it turns out that the log laws can be proven using the index laws, which is why I feel like they're so well related to each other. And the trick is to make some substitutions in the index laws. Here I sub m is equal to log base a of x into the m's here. And I also sub n is equal to log base a of y into the n's here. So notice how the m here turns into log base a of x. Log base a of x. It's not letting me highlight, apologize. And the n turns into log base a of y, and log base a of y. Now, but using the inverse relationship that I mentioned earlier on, and you may have copied down when I told you to, but if you don't, just go back to a few slides. I basically now use this identity here, and using this property, or identity, whatever, what I get is that a to the log base a of x will basically turn into x by itself, and a to the log base a of y will similarly turn into y by itself. So I go from the reddish equation to this black equation down here. And then the trick is now to more or less just use the definition of the log, because the idea is that we now have a to the power of something here. And the trick is that if I want to get rid of the power, then I can just, we'll leave obviously the thing in the top as is. But then on the left, I'll now put down a log base a in front of the xy. But when I do that, I effectively obtain literally what I was looking for. And that is the proof of the first log law. Now, keep in mind that obviously I do not expect you to memorize this, and I don't believe QCAR should either. But the reason why I go through this is just purely to show you that these log laws are actually a real thing and not just somebody's made up expression that we expect to believe. If you're interested in it, you may want to try proving it with the other log laws as well. But if you're not interested in that, it doesn't matter in my opinion, so long as you're interested in this one at least. But yeah, that's basically motivating the first few log laws, and also one more log law called the change of base law. And this log law, it's more unique from the rest because, well, it's not related to an index law, but it's special because it's more or less a way of changing the base of a logarithm. Because changing what's inside the logarithm can be done using the traditional log laws, but if you wanted to go from a base, like say 2, to a base 3 log instead, this relationship is what lets you do it. And the idea is that what's inside the log goes in the new base log on the top, and the original base gets moved here, and basically you take the log base b of it in the bottom. Again, this is on your formula sheet, so you don't have to memorize off by heart, you just need how to use it. So, there aren't that many questions specifically where this is useful, and because in the technology active section you have a calculator that can do logarithms of any base for you, there's no big of a deal. But every now and then for the technology free section, using the change of base law might make your life a bit easier. And this is one example of where I would personally use it at least, because, I mean, if I were really good at using fractional powers, or if you are, you could jump from this line straight to that line in one go. That's perfectly fine. But I personally feel as though if you use the change of base law, converting to logs of base 2, the question becomes a little bit more manageable. Because when you do that, you can see that, well, I know that 32 is definitely a power of 2, is equal to 2 to the 5. And I know that 8 is also a power of 2, is 2 to the power of 3. So then I see that, well, since 32 is the 2 to the 5, the log base 2 of 32, I know will just be the power on the top, i.e. 5. It's not highlighting for me properly. And basically a similar thing on the bottom. So log base 2 of 8, 8 is 2 cubed, so therefore log base 2 of 8 should be 3. Again, these are just using how logarithms work from units 1 and 2. But notice the reason why I use a change of base is more or less because I see that they're both powers of 2. Whereas trying to get 32 as a power of 8, yeah, I didn't think that would be something that was, easy. So I chose not to. This slide, you don't have to worry too much about. I've already mentioned the important part. So you may want to, pause the video at this stage to digest everything that's now, but of course I'll keep going. And the next thing that I more or less covered was basically dealing with graphing logarithmic functions. So, well, you should be familiar by now with the graph of an exponential and also its asymptotic behavior along the x-axis. And it turns out that the graph of y equals log base a of x is obtained by doing a very weird reflection that you may not have seen before. The idea is that you reflect it along the line y equals x, so you actually reflect it on a slanted line to obtain this curve. Do I expect you to do that all the time? Obviously not. This is just me showing you where the curve comes from. Now, is there a reason as to why this happens? Yes, there is. Basically, the trick is reliant on inverse functions, but don't worry too much about that. But when you do this reflection, what you'll notice is that for the log curve, instead of having a y-intercept at 1, you'll now have an x-intercept at 1. Instead of having an asymptote along the x-axis, you now have an asymptote along the y-axis. And furthermore, you can see that the domain of the original curve, the exponential, the domain of the exponential was all real x. It turns out that for the logarithm, the range is going to be all real y. Furthermore, you'll find that the range of the exponential was all y greater than 0. You'll find for the domain of the logarithm that becomes x greater than 0 instead. So in a way, the roles of x and y do swap, and that's basically what I've summarized in this table here. This is something you can consider after Unit 4. I wouldn't worry about that right now. So this is more or less an example of how you can plot y to the log base 2 of x. You may find interesting how this table of values is sort of the reverse of the table of values for y equals 2 to the x. You literally just swap x and y around. But it more or less gives you this kind of curve like this, and it does look like an exponential if you think about it. It's just that, it's not literally an exponential because it's been flipped very weirdly, but it does take a very similar shape. So this is more or less the type of curve that you should grow comfortable to sketching throughout your course. You should get very well accustomed to this by the end of it. But of course, obviously, that's not all they're going to make you sketch. They're going to add in a whole bunch of other stuff just to, make life hard, I suppose. Because, if you just sketch only that, the QCE exam might be a bit too easy. So, for simplicity, we focus on the natural domain. And this is just a reminder that when it comes to horizontal translations, recall that if you consider the graph of f of x minus b, it will be the same shape as y equals f of x, but you shift it to the right by b units when there's a minus here. Just don't forget that. This stuff down here, you don't have to worry too much about. That's just a bit of side remark. So here, if I tell you to sketch y equals log base 2 of x plus 1, well, you will start by looking at your graph of y equals log base 2 of x, or you will keep a mental note of that. But then, because here we have a plus 1, our b in this expression would be minus 1, and hence you're translating to the right by negative 1 unit, which really is saying you translate to the left by 1 unit. So hopefully you'll be able to be comfortable at accepting that. And then, for vertical translations, on the other hand, if you have a plus c on the end, then you are translating it upwards by c. Again, this is just a recap, but you do the same thing here. So here, if I give you the graph of y equals to log base 2 of x plus 1, what you do is that you take your original graph, and now you shift it up by 1, which gives you this one. It may not be obvious to see that the graph has been shifted upwards by 1, but I promise you it is. And you may want to verify in your own time that in fact the intercept has now been moved to x equals 1/2 instead of x equals 1. And just as another example very quickly, of course, you don't have to just be doing translations using only your, as in like only left or right or up or down one at a time. You may of course be given questions that require you to do translations in both directions, so long as you are comfortable with that, everything's all good. Generally speaking, I recommend translating left and right before you translate up and down. That's my recommendation. Sorry, bit of an accident just now. It's my recommendation just because it more or less makes life easier for some of the other topics. But pretty much, so for this question, I mean, that's all there is to it, you just do it. So here you have log base 2 of x minus 1. That means you need to move it 1 unit to the right first, and that's why, you know, the asymptote be moved as well. And then the minus 1 outside here says after that, now translate it 1 unit downwards. So this shape is no longer, you know, obvious, you gotta take your time to think about it. You may want to try and find the x and y intercepts explicitly after the next section about solving equations. But apart from that though, the shape is still the same, there's not really that much more to it otherwise, so at the very least we're lucky in that sense. Now, dilations, I mean, in all honesty, you may want to jump this section because dilations aren't explicitly covered in the syllabus, and in my lecture, due to the interest of time, I chose not to cover this section as well, for the same reason. But I will make a bit of a remark about how they work in the recording, more or less for the interested audience. And dilation, they more or less do their job the same old-fashioned way. Here, this is a dilation where you stretch outwards about the x-axis, so these y-coordinates go further up, and these y-coordinates go further down. More of a classic thing, nothing fancy here. And of course, you also have dilations where you instead basically just, you know, do dilation about the x-axis instead, and that will be a dilation inwards, outwards about the y-axis. So because here we have a 2x, we need to dilate it inwards to the y-axis by a factor of 2, and that's why, you know, it looks a bit more squashed towards the y-axis, right? But if you really look at it long enough, you'll find that this dilation looks a lot like a translation. You might need to stare a lot to see that, and it's a bit hard to see down here, but once you get further into it, you'll see it does look like the red graph is also literally just the blue graph moved upwards by 1 unit. And for the record, this is no coincidence. The idea is that pretty much, I think the reason why they don't cover dilations about the y-axis is because they can actually be represented as a vertical translation anyhow, and to do that, you more or less need to use the log law given by this. So you may not want to read the proof, and in all honesty, don't worry about it if you're not interested in it, but it basically says that if you ever want to sketch this type of function, what you can alternatively do is use the sum log law, so that's log base a of bx is equal to log base a of b plus log base a of x. And once you do that, you can basically forget all about dilations about the y-axis and just turn it into a translating up and down problem. Just a nice thing to note. And then, so before I talk about the other dilation with the vertical again, about the x-axis, my jargon is not going well tonight. You may also be given a question like, say, this one. So this is just me giving you a graph of y equals log base 3 of x instead, and notice how the table of values has now changed as well. It more or less takes the same shape as y equals log base 2 of x, it's just that instead it looks a bit more squashed downwards. But depending on how well you know the change of base law, you'll find that basically changing the base of a logarithm has sort of the same effect as doing a vertical dilation, a dilation about the x-axis. And this is something that honestly takes a while to understand, and in all honesty, I would rather just skip it if I were you. So like, if you don't like this, please don't worry about it, just move on. But if you're really interested, take a bit of time to think about the reasoning I give on these slides to relate between how changing the base of a logarithm has a very similar effect to literally just doing a dilation about the x-axis, i.e. a stretch. But again, I don't think I'm going to worry too much about it. We won't discuss reflections in general case because, again, these were not specified in the syllabus either. I am now just going to move on. So the next section was regarding solving equations that involve exponentials and logarithms. So I firstly show some motivating examples with exponentials. In general, when it comes to exponential equations, if possible, you should try to get the left-hand side and the right-hand side to all be of powers of the same base. Here it's possible because 4 is a power of 2 and 8 is also a power of 2, so therefore I can make everything in terms of powers of 2s. And then once the two bases are the same, all I need to do is just basically set the two powers equal to each other, at which point I can just solve the equation through more classical means, right? It's a linear equation now. That's basically the technique here. But of course, if you look at the next question, obviously you can't get a common base between 4 and 3. So when things go bad, the trick is more or less just to use your logarithms where possible. So you obtain, instead of having that, you now move a log base 4 onto the right hand side. And then, look, so obviously you would want to move the 2 to the other side by adding it. And then you want to get rid of that 2 by dividing it down. And your answer is going to look like that, and yes, it's definitely a very ugly answer. But in all honesty, there is nothing better that you can do. You kind of just have to accept this ugly answer and roll with it. I did pose a challenge here. This is only for if you're interested in it. If you're not, don't worry about it. But the challenge is basically, can you turn that expression into that expression? Or can you just like ignore my working out and get that expression instead? I won't show the answer here. If you're interested, you can ask me on the forums. I will move on at this stage. The important thing is that you can understand that expression at the very least. And then, just as a side remark, you may have some little tricky questions where you have powers of... We have an exponential to the x here, but this is just a bit of a cheeky thing that sometimes they like to do, where they put 2 to the negative x on the other side. And the trick, more or less, is that if you do that, just multiply both sides by 2 to the x. And the thing is, on the right-hand side, what happens is that if you multiply 2 to the x to the negative x, they will cancel each other out. Think about why that's the case, but they'll cancel each other out. So you're left with a 1 here. And therefore your equation turns into that. And naturally, because you want to get the x to be by itself, you would divide the 16 across. That will give you a 4 to the x here left by itself. You may wonder why that's 4 to the x. But you'll definitely have 1 of 16 on the bottom. Just as a side remark though, you don't have to change it to 4 to the x. So long as you can use your index laws to deduce that 2 to the x all squared is to the 2x, you should be able to get to the final answer of x equals negative 2 anyway. But, I mean, I was just more or less rushing some steps here. And I do apologize, in the lecture I did write the working out now, but right now I don't have the resources to write the working out, so sorry. But basically, more complicated questions that involve exponentials and logs, well, what you'll find with them is that they like to mix in quadratics. So this equation is a very classic scenario where basically using quadratics will get you the answer in the end. And some people that are really well accustomed to doing this just jump straight into it without doing this sub. But I basically make this sub mandatory just so that you guys understand what's going on. So I basically give you the substitution u equals 3 to the x for this problem. And the idea is that, well, as you can imagine, this 3 to the x here will be subbed away for u soon enough. But this 9 to the x can be subbed away for u squared. And this is the reasoning behind it. The idea is that you know that 9 is equal to 3 squared, so you can just replace that as is. Using your index laws, you know that 2 times x is going to be 2x, so you can do that. But then, you can use your index laws other way around, because, again, x times 2 is 2 to the x, so if you use the index law the other way, you can basically get it to look like that instead. And notice how it really is just the 2 and the x swapped here. But then, once you do that, now that you see 3 to the x, you know that you can sub that in for u squared. And that's basically understanding why the substitution works. However, well, obviously what's interesting is what happens when you now use it. So when you sub it in, the 9 to the x becomes u squared, the 3 to the x becomes u, and hopefully, as you can see now, you have indeed ended up with a quadratic. So provided you recognize how to factorize this expression, you'll be able to obtain your final answers. But after you do that though, you gotta keep in mind, the original equation was in terms of x. Notice how once you do this, your solutions are currently in terms of u. So to get your solutions back in terms of x, you now need to undo the substitution. So here we have u equals 8 turning into 3 to the x equals 8, and that will give x is equal to log base 3 of 8, using our techniques that we saw earlier. And here, for the other one, this is more or less just a case of identifying that anything to the power of 0 is equal to 1. Or, you can get this through other means as well, but that's how I like to think about it personally. And this is more or less just another example following the same pattern. So if you understand the previous example, you will eventually be able to understand this example as well. The only difference I want to mention with this example is that you may get negative solutions for u when you go through this procedure. And you've got to keep in mind that when you sub back in, so here we have u equals 5 to the x. If you sub u equals 5 to the x back in, you get 5 to the x equals negative 1. But the trick is to identify that if you have an exponential equal to a negative number, that will never have any solutions. So that's something that you have to watch out about. So that's basically the indices side of things. On the other hand, you just have logarithms. For logarithms, well, where possible, the idea is that you just get rid of a logarithm as soon as possible using the definition. So remember that if x is equal to log base a of b, then a to the x equals b. So here for this expression, because I have a log base 5 right now, if I want to get rid of it, I need to move the 5 to the other side, but then the minus 1 now goes inside the power. And then so you get 3 to the x equals 1 over 5, i.e. x equals 1 over 15. This is more or less just another example of the same thing, but it just shows you they might need to do a bit more work every now and then. If you have stuff outside the logarithm, just get rid of that first. So here, notice how the 2 is outside of the logarithm here. So I did the natural thing of dividing the 2 across. And then, once I had the log by itself, I moved it to the other side. So going from here to this line, what I'm really doing is I'm saying that, well, okay, 2x minus 3 should therefore equal to 4 to the power of 3, which is 64. Once you solve that, you now get 2x minus 3 equals 64. From then on, everything is again just linear equations. And then you have some other equations where instead of having just a constant by itself on the right hand side, like minus 1 and 6 here, you might get the same logarithm appearing on the other side as well. When that happens, in general, as a rule of thumb, you are safe to just take the 2 logarithms out, or rather get rid of them. So what happens is that in this expression, you literally just look at what's inside the log in the left-hand side, and what's inside the log in the right-hand side, and you make them equal. So you are allowed to do that. There's no problem with this whatsoever. Notice how, in this sense, it's quite similar to how, for the exponentials, where possible, we just took the powers as well. Similar concept. And now, for harder questions that involve equations on logarithms, again, you might see quadratics come in play. But the idea is that the harder questions involving logs, well, what typically happens excuse me, is that you basically have more than one log appearing, and you can't do this trick, where you just like move the logs on one side. Instead, you might have like say 2 logs added, or like 2 logs minused, or some extra numbers here. And pretty much the trick is that whenever you can't, use this slick trick, you just use your logarithm laws to combine all the logs together first. So notice how this turns into x times x minus 3 in the next line. And then once you do that, you now you start by proceeding through traditional means. So here the log base 2 gets moved to the other side, so this now becomes 2 to the power of 2, which is of course 4. And you solve that using your unit 1 and 2 techniques, and you get a quadratic. But notice how you get 2 solutions, x equals 4 and negative 1. But what happens is that this negative solution is not going to be nice. So this is a very overcomplicated explanation here. What I generally like to think about is this thing in green instead. You cannot ever have a negative number inside a logarithm. So the thing is, when you ended up with a solution x equals -1, well, if you plug that back in, you will get log base 2 of -4 plus log base 2 of -1. That there is not okay, because you're now taking the log of a negative number. So because you run into this issue, you more or less have to ditch the solution x equals -1. It basically no longer exists. Sorry. And you end up being left over with only your solution x equals 4. Notice how with x equals 4, you don't run into the same issue, because if you sub 4 into here, you get log base 2 of 1, that's not a problem because 1's positive, plus log base 2 of 4, and that's also not a problem because 4's positive. So in this case, you don't have to throw out the solution x equals 4. But of course, x equals -1 is the problem, and why do I talk about this is just so that you understand why we only throw out one solution. Yes, in theory, you may have situations where you have to throw out both solutions, and therefore you end up with no solution at all. And you may bump into situations where, so not that one, but you may bump into situations where you end up not having to throw out any solutions if you're really, really lucky. And that's something worth mentioning as well. But in general, that does not always happen, so you should definitely watch out for it. And this is just a bit of a berserk example. It's not really that much to say, but it's more or less, again, just showing that if you have coefficients in front and you can't, cancel the logs out, just move the coefficients in. So here, the 2 gets moved into the power of x, and hence you get x squared appearing. So on, so on, forth, you eventually boil it all the way down to here. But in a similar way, you also have the can't log a negative problem, and you end up having to throw out the solution x equals -5. But really, I know the base 2019 looks intimidating, but it's more or less a similar problem to the one that we saw just now. I already mentioned that. I do have a remark that I do want to make in that you don't always bump into logarithms. I mean, no, you do bump into logarithms, sorry. You don't always bump into quadratics, rather. And this is an example of where instead of having quadratics, you end up with a fraction. I will make a remark though, whenever you use these log laws, like when I get x equals 5 on 6, I really should sub that back in as well, at least it's my recommendation. But though that is my recommendation, I clearly did not do it here, so I am a bad student. But again, for problems like these, I will more or less encourage pausing the video and trying to understand what's going on. So here, I use the difference log law to turn it into a quotient. I do a fraction, and I move the log base 5 across. That's where I get 5 to the power of 1 from. So that's more or less it about logarithmic equations, and again, another reminder, pause the video if necessary. So the next thing on that is more or less the last main thing in the logs topic, and that's logarithmic scales. And I mean, I spent a bit of time motivating this during the lecture as to why we deal with them, and the idea is that they're loosely what's focused on orders of magnitude instead. For the sake of the recording, I won't really spend too much time on that. You can Google search orders of magnitude. I believe there's also a Wikipedia page if you want just a very quick summary about it. But it more or less turns the issue about some kind of relative size, but rather, I mean, because a scale is what's called a multiplicative scale rather than additive scales, so it focuses on things in a different perspective. But I think it's easy to show what's going on through mathematical means rather than go through motivation right now. And more or less the contrast between a linear scale, which is more or less what we're traditionally used to, as opposed to a logarithmic scale, is more or less in the fact that one of them is a linear function, whilst the other one's a logarithmic function. Surprise, surprise, that's why the wording is what it is. So, but the thing with linear scales is that if you think about it, suppose you have a linear scale to start with, well, rather, you have this kind of expression, you have two quantities, y and x, and they're related by the expression y equals mx plus b. Should have used plus c, my apologies, but whatever about that. Well, here's the thing, if I try to increase the value of x by, say, 1 unit, so if I make x go up from, say, like 1 to 2, then the value of y, you would expect that to instead increase by m. So if you originally had, like, say, for example, 3 for your y value, it would then become 3 plus m. And it also goes the opposite way in that if you instead increase y by 1 unit, you have to offset it somehow by increasing x by 1 on m. So you just literally add 1 on m to x instead. Now, whereas for logarithmic scales, it's more of a multiplier thing. And I did spend some time trying to go through the proof as to why this sort of thing happens, so this is something I don't feel is worthwhile for the recording, but you will probably need to spend, a reasonable amount of time trying to go through this proof if you want to think about it very carefully. But essentially what happens is that instead now, if you decide to increase y by 1, then what happens is that you don't add something to x to sort of offset it, but rather you have to multiply x by a. So for example, if, you started with y equals 2, and then you go to y equals 3, if your original value of x was, like, say, 5, your new value of x will be 5 times a. And the idea is that that's more or less for when you increase y by 1. Instead, if you increase y by some random value, n, what happens is that rather than just, again, adding n to x, you have to multiply x to a to the power of n instead. So, for example, if you started with a y value of 3, you started with y equals 3, and then you turn that to y equals 6, so you increase that by 3, then if your original value of x was, like, say, 2, then your new value of x will actually be a to the power of 3 times 2, i.e. 2a cubed. So you really have to write this out to understand it. Like, just saying it's not going to be enough. You really need to write it down and think about why this kind of thing works as it does. And don't worry too much about this, but basically the example that I showed during my lecture was a base 10 example, so I subbed in a equals 10 here. And I'll jump straight to the point, but, well, basically the idea is that this is the pH example, so pH turned out to be measured in terms of the concentration of a hydrogen ion. But there is a negative sign here that we didn't have for the original model, and that does change things up a little. So what happens is, so here's a sample question. Given the concentration of hydrogen ions, H denoted square bracket H+, the pH of a solution is given by that formula, so that's my question. Now, a strong solution of hydrochloric acid was recorded to have a pH of 3.2. The first part just wants me to calculate the concentration of the H+ ions, and that's something that would be impossible without the calculator, just for the record. But it pretty much is just an example of literally solving definitely logarithmic equations, as we saw just now, because if we sub in pH equals 3.2, we just get 3.2 is equal to everything else. And to solve this equation, you now just follow the classic principles. You move the negative across, so you get that. And then, now that you have the log base 10 by itself, you can move that to the other side, so the negative 3.2 goes into the power, and 10 becomes the base. So the concentration of a hydrogen ion, well, the exact value will be 10 to the minus 3.2. And the idea is that, well, because I said 3 significant figures, I gave you an approximate value as the answer. So that's just basically the last section all over again, but what's of more particular interest is the second part. We say that now the solution was diluted to a pH of 5.2, meaning that although the original pH was 3.2, the new value is 5.2, and the question is, without any more calculator work, write down the new concentration of H+, i.e. what this value now is. And there's many ways of thinking about this, but the idea is that we can follow some line of thinking similar to what we had earlier, but you got to keep in mind that the negative sign is going to affect things a little, because the fact that we have minus log base 10 of H+, means that by increasing the pH by 2 here, notice how it's gone up by 2, 3.2 to 5.2, yeah? If I increase that by 2, then the negative of that thing increases by 2, i.e. this whole thing increases by 2, meaning if I block out the negative, that inner expression here actually decreases by 2. And that's one way of thinking about it. Alternatively, that increased by negative 2. So the idea is that because it increased by negative 2, it turns out that the concentration of H plus should therefore increase by a factor of 10 to the minus 2. What I mean by that is that to my original value of the concentration of a hydrogen ion, I now need to multiply 10 to the power of negative 2 to it, following the same line of thinking that I did earlier. And that's why this 6.3 1 times 10 to the minus 4, well, if you multiply that by 10 to the minus 2, that now turns the power on 10 to minus 6 instead. And that is my answer. Now, I do want to talk about some general advice that I also gave during my lecture, but I'll probably gloss over this because I know you can read this in your own time as well. But it's worth mentioning anyway, just because, why not? First and foremost, important reminder, remember, you're not the only one taking the new syllabus and the new QCE system. I know it's definitely really, really hard trying to deal with everything all in the one go, but remember, you are not alone in this. You should never feel that way. Everyone's going to be in the same boat, and the ATAR will somehow cater for it. Because the idea that the ATAR is actually not a mark as well, it's really a rank. The ATAR is more or less a measure of just how many people you do better at in the state. So I gave more of an example. For example, say, let's suppose the max mark for math methods in the country was like 75, and you came out getting a 74. Well, you'll probably still be considered like, probably a god among your peers. You'll be considered someone with a very high rank. So you can get a high rank despite the fact that your marks might be hit by the system, so just bear that in mind. So emphasize on that, you should do as well as you can do, and like, as long as you've done your best, that's all that matters. Everything else, the system will at least somehow cater for it for you. So that's my point. This early on, so long as you know that you have, your assessment structure being half internals and half externals, good enough. What I have right now is more or less just some early preparation strategies you can consider for the externals. I won't go into much depth, but basically some things I felt like worth mentioning are that 1, focus on trying to be consistent with studying. Don't try to study in, big blocks because it just drains people out. I genuinely recommend just doing enough math every day to keep your brain, constantly active and not burn out. Breaks, something that, you'll probably develop more into throughout the year, but breaks, so long as they're controlled, you have breaks that are reasonable time spent during the day, provided you do that, it's, in general, a really, really good thing, because obviously if you spend a huge break just wasting time gaming, then, that's a lot of time going out the window, but, seriously, having small-minded breaks, it will help you get your focus back, surprisingly. Whilst you feel like you're gonna just, give up on stuff, just take a little break, and then you'll find that you have more energy afterwards to get straight back into it. Balance, just a little thing I want to mention, make sure you're not only studying for math, that's pretty much it. And the idea is that studying is a bit annoying because everyone's strategy is different. What works best for your best friend might not, in fact, be the best strategy for you, and that's something you definitely have to watch out about. Please try to, throughout the year, find what studying habits are going to work best for you. I do have some suggestions about what you could consider, but that's not to say that all of these will in fact be useful for you. In fact, not all of these specifically were useful for me, but it's just something that's worth thinking about throughout the year. Alright, so I'll talk about calculus. I'll probably skip the applications, I apologize for that, but I do want to talk about at least the differentiation parts today. And well, basically during the lecture, I didn't really have time to go through the derivations of the whole calculus-based stuff, so I'll skim through it a bit briefly during the recording whilst I can. Number 1 is firstly that, well, we want to start by attempting to differentiate any exponential functions, and you'll find that as far as math methods go, we can't differentiate everything. So the idea is that, because you can't use the power law here, because exponentials are clearly not polynomials, you need to use the first principles definition of the derivative again, i.e. this limit. And when you do that, you find that you do get some very interesting expression if you try differentiating a to the x. It turns out you get a to the x itself times some mysterious limit. And this limit is something that turns out to not be so easy to evaluate. But what's of particular interest with this limit is what you can do with it, because, okay, so here's a GeoGebra simulation here. What the GeoGebra simulation does, if you click on it, is that it will take you to here, and this is more or less just simulation to basically just get GeoGebra to find an approximation for what the limit equals to for different values of a. and the limit is basically determined as L. The y-intercept here is basically the limit. Don't worry too much about y, just take for granted that it is. But the idea is that if you try moving your value of a very close to this number 2.71828, 1828, etc, etc, you'll find that the limit turns out to get to a value really, really close to 1. And that's quite interesting, because if the limit's equal to 1, i.e. this expression here, if that's equal to 1, then when you multiply it out, the whole thing should disappear, right? So ultimately, you're left with f dash of x, f prime of x, is equal to a to the x itself. So the idea is that, well, here's the thing. Whatever that constant is that makes the limit equal to 1, we make that number e. So e is basically internationally called Euler's number. It's a very famous number, and it's irrational, much like pi. It satisfies just some very nice fancy results here. But the idea is that because this number e is rigged to make that limit equal to 1, if I try now differentiating specifically e to the x rather than a to the x, I can now go through the whole first principles procedure and actually get somewhere. So at this point, it's definitely worth mentioning that throughout this course, I believe you will only have to differentiate exponentials if the base is e. If the base is a number, I do not believe you have to worry about it at all. But the idea of this function is special because if you differentiate it, guess what? The derivative is in fact the original function, which is really, really powerful. So because of that, for some magical reason, they try to call this function the exponential function, rather than just our exponential function, an exponential function, whatever. But pretty much from here on, I just have a whole bunch of examples that demonstrate what you can do with it. So these you can go through in your own time. They more or less just show that if you want to differentiate with an exponential, you can just follow the exact same laws of differentiation as you've seen in the past. So here we have differentiation term by term, as this is called, because you just differentiate one at a time. You also have the chain rule, and using the chain rule, you can also do computation like the following. Here you will have to compute the derivative of the inside as well, which is going to be, the derivative of that will be a, and then times it by the derivative of the whole thing. You can also have some other computations, but every now and then, just with exponentials, I feel like it's worth mentioning, oops, sorry, the typo here. I feel like it's mentioning that if you ever bump into situations where you have a power on an exponential, you can always just use index laws to put the power in. So this 3 can be shoved in here to become 3 lots of 2x minus 1. And that's where my 6x minus 3 comes from. And then from there on, you basically use the same law above and just differentiate using the old chain rule. And of course, you may have even more bizarre computation with the chain rule. So for example, here, the derivative of the inside function, which is x squared minus 4x plus 5, is 2x minus 4. But then again, the derivative of e to the x is itself, so therefore you end up with that expression. So pretty much this is not something that you're expected to get on the spot, but after you've done enough practice, that's when it becomes second nature to you. And there's just more examples here, like they're not really worth me going on for much longer. This is just an equation of a tangent question. And that more or less is the basic idea. And also in regards to logarithms, because I want to give these at least a mention before I end the recording off. In terms of a logarithm, well, again, typically you'll only be working with the logarithm corresponding to, surprise, surprise, the base e. And this logarithm you'll find in mathematics tends to be called the natural logarithm, and is commonly abbreviated to ln of x. It means logarithm natural, as you expect. And you will do calculus on this natural logarithm instead, much like how you do it with the base e exponential. Just as a quick remark, with the natural log, it does satisfy the same properties as many of the other logarithms. So for example, the definition, still the same thing. The inverse relationships, they also hold. And it also satisfies the change of base law. And it also satisfies every other logarithm law that I have not mentioned. So it's just really a logarithm to base e, where e is this very special number that I just introduced at the end. Now, don't worry too much about the derivation of the logarithm. The derivative of the natural logarithm. What's of particular interest is just the final answer, and it's that if you differentiate y equals ln of x, you actually get dy dx is equal to 1 over x, which is, of course, your reciprocal function, right? It's your hyperbola. But then once you know that result, everything now is practically the same again. So here you have, for example, term by term differentiation, nothing fancy. You also have the chain rule. Of particular interest with the chain rule, though, is that if you do use the chain rule, you do get one nice result, in that the derivative of log of a times x, well, the derivative of the inside function, which is the derivative of ax, is just a, so therefore it will be a, times the derivative of the whole thing. Well, the derivative of log of x is 1 over x, so the whole thing here, in some sense, will be 1 over ax. But then, by some magic, guess what? The a's cancel out and you're left with 1 over x anyway, which is exactly the same thing as differentiating log of x itself. Just a very nice quirk to keep in mind. But of course, if you have to say x plus b, you just have something much more ordinary. So this is really just the same thing. I know I'm rushing at this stage, but I promise you, with enough practice, this will start becoming more second nature. And of course, you can always pause the video if you need be, right? The chain rule can obviously get a bit more berserk. So if you use a chain rule here, then the derivative of the inside function, i.e. the derivative of x cubed plus 2x, that will now be 3x squared plus 2. And then the derivative of the whole thing, well, the idea is that basically the inner function always ends up on the bottom with logs. That's a pattern that you'll just start getting more accustomed to. So there's your final answer for that one, part 1 of this example. And part 2 of this example is more or less just to demonstrate that not only can you use the chain rule, but you can also use the product rule as well, and also the quotient rule. So this example was a bit tedious, and again, I'm not going to go over it in much detail right now, but this problem actually requires you to use both the product rule and the quotient rule, because for the derivative of the top function, you need to use the product rule to differentiate e to the x times log of x. And remember, for the product rule, depending on how you learnt it, you differentiate e to the x and you leave log of x alone, they're the first one. And then you leave e to the x alone and you differentiate log of x, and they're the second term. And then once you do that, you now plug your product rule result into the quotient rule. So this is some really, really messy algebra, and like not something that I expect you to know how to do instantly. I would recommend having a lot more practice with differentiation with logarithmic exponentials before doing this question. But it's just one nice one taken from the New South Wales paper, and that I felt is worth showing to you guys, or at least if I had the time to, I would have shown you guys. But the one thing I want to mention is that with log laws, sometimes it may be tempting to use the chain rule straight away, but if possible, try to use log laws first. So like this example has been rigged because you have log of square root of x squared plus 5, and if you jump straight into it, you get a very, very nasty chain rule computation. But if you instead use log laws, you'll find that the math is much easier. So what I do here is that I identify that the square root can be written as the power of a half, and that power of a half can then be moved in front. So this 1/2 now is more or less just a constant, and we know from units 1 and 2 that when it comes to derivatives with constants, we just ignore the constant and just differentiate whatever's left over, and this can now be differentiated using a much easier chain rule application from the old manner. So the derivative of x squared plus 5 is 2x, and then you have the thing on the bottom as well. You get used to that pattern, like I said. I apologize, there should not be a square root here. That is definitely one huge typo. The answer is just x divided by x squared plus 5. I apologize deeply for that. I don't know how that ends up here. The correct answer is on the previous slide, so there you go. But that more or less illustrates the concept for you, I hope. Or at least, it eventually will, right? Even if it doesn't right now. I'll just make a note that, although I'll make a remark in that you probably won't get questions this stupid in an exam, but because you can use log laws, just for something really, really creative, I can show you that if you have something very, 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 very messy inside a logarithm, you can actually compute its derivative much more easily, so long as you use log laws. Do I recommend trying to go through this problem right now? Probably not. Maybe towards the end, if you remember right before your VCE exam, you might want to have a look at this just to, see what see how your nightmares could come true, I suppose. But it's just a very nice problem to see just how powerful things can be when dealing with logarithms and using logarithm laws effectively. Yep, and unfortunately I won't have enough time to go through this, but this is just more or less a rates problem, which you can try working through in your own time. But otherwise, that is pretty much all I have. Don't worry too much about this. So if you have any more questions, if, for example, you think the recording's not clear enough and some stuff you want even more elaboration about, please hop online on the forums and ask. If you have something that's not content related and it might involve like sensitive information, for example, your marks, feel free to just send me a private message. This is my username on the forums. But other than that, that is pretty much everything I wanted to cover for now. So thanks so much for zoning in for so long. If you have gotten to here, I genuinely appreciate it. I do understand that this was definitely at a much faster pace than what I was going at in the actual lecture. So if you don't understand everything in this recording, I really don't blame you. But at the same time, also, again, one, ask me a question if you want to. And two, you can always just watch that bit of a recording over and over again until you finally get it. So do it more step by step. But otherwise, I'll end it here, and please take care, everyone. Best of luck in your studies.